Okay. Hi, everyone. I'll introduce our next speaker. His name James. He came from London, United Kingdom, so he's native speaker. Sorry for my pronunciation.
It's all good. It's fine. I'm your guest.
As I said, James living in London. He's working in a company called SitePen, and also he is Google Web Developer expert, by the way. So welcome.
Cool. Yeah, so thanks for having me. It's really great to be here. First time in the Ukraine, first time in Kharkiv. So yeah, thanks so much for having me along at your conference. This is my presentation. We need to talk about the main thread. I hope that the clicker will work and let me change the slide, because otherwise we're going to be stuck on this one. Okay. Yeah, so my name's James Milner. I'm a software engineer at a company called SitePen. We're like a web app consultancy. We mostly work on enterprise web applications. So working with like a lot of like banks and hotels and like these kind of big enterprise kind of organizations. I'm also a Google developer expert for web technologies. And I also tweet at my handle, which is James L. Milner, if any of you are on Twitter. So let's get started. So what I want to do is kind of take a step back and go back to kind of the early days of the web, not right to the beginning, but to kind of the first sort of like commercial websites, and kind of think about the kind of things that we were building at that point in time. Well, not me, I would have been about 7 years old, but these are some examples of the kind of things that were being built back in the kind of mid to late 90s. And you've got up there things like the Wikipedia page, GeoCities, if you remember things like GeoCities, like the AOL website, Yahoo, also the Space Jam website, if any of you remember the ridiculous film that was Space Jam. It was like a comedy that featured Michael Jordan and the cast of Looney Tunes. It was just ridiculous. But their website is still online, and you can still go on it, and it still works, which I think is just kind of like a really cool testament to the power of the web and the backwards compatible nature of the web. And kind of as we've moved forward, we've decided not to break things, which is pretty cool. But the web's kind of changed quite a bit, and kind of the things maybe that we build nowadays, or the kind of experiences that we provide to users on the web is just different to what it was back then. It's kind of like a much richer experience, much more of an app-like experience, I would say, for certain sites at least, with lots of interactive elements, things like animations and just more kind of complex interfaces and interactions. So I've just got some examples up here. It's like Google Docs, TweetDeck, the Skyscanner website, Google Maps. Like all of these things are kind of, to me at least, feel like a lot more of like an app-like experience. Yeah, like a lot of websites have essentially become web applications. We kind of treat them more like applications rather than as documents, right? Because you can, and the reason for this, I think, is you can just do so much more with the web nowadays. Like the standards have progressed like so much, and there's so many more like capabilities on the web. So obviously there's elementary things like being able to update the DOM or styling, but there's also like more complex things like like the introduction of Canvas and WebGL. We can make things like games. With web audio, we can do all kinds of cool and crazy things with audio. There's all kinds of different, like these are just like a handful, these are just like some of the APIs I picked off the Mozilla Developer Network pages. We can just do a whole host of things that we couldn't necessarily do before. But as we've kind of like pulled more logic into the client, and we're doing more on the client in the browser, we've also increased the amount of JavaScript that we're using in our pages. So this is a graph which I pulled out of the HTTP archive, which essentially can just analyze all of the pages. So this is the top 1,000 pages on the web. And what's really interesting is that back in 2011, it was the average amount of JavaScript we were shipping to a page was about 79 kilobytes. So around the same time last year, in 2018, we were shipping about 558 kilobytes. So that's about a 7-fold increase in the amount of JavaScript that we ship to clients on average. So yeah, but all this kind of JavaScript doesn't come without its additional cost. Because I think like one thing that a lot of time gets forgotten about JavaScript as an asset on the web is it's not just like the download times, right? Because you've also got to pass that JavaScript so that it can be turned into the like a data structure that of tokens that can be used by the compiler to turn it into a program. So it's kind of like this 4-stage process. It's not just like downloading it and like there's your JavaScript. So there's this added cost that maybe doesn't come with other kind of static assets on the web. And this process isn't always super snappy, especially on kind of low-powered devices, maybe like low-end Android devices that are increasingly popular, especially in kind of like emerging markets. And the result of this is we've kind of ended up on certain sites and certain experiences where we end up with these slow or kind of janky user interfaces. Like, I'm sure we've all had an experience where we've gone to click on something on the web and it's just like not responded, or it's not responded in a way that feels smooth or kind of immediate. And this is like, we kind of see this a lot in server-side rendered pages, because you get the page, you get the HTML, it all looks like ready, but when we go to click on something, the page hasn't hydrated, like we haven't registered the callback handlers for the clicking events. And this is what leads to this kind of initial like jankiness kind of on load. This can happen like later in the page as well. If we have we're trying to do a lot of things at once, then we can cause a blockage there. But it's kind of most prominent on page load, I would say. But luckily, there's kind of ways that we can measure this, and we can kind of account for this a little bit, or try and kind of stop it. So 2 metrics that I kind of want to point out here are, first of which is time to interactive. So time to interactive is the amount of time it takes to respond, for a page to respond to a user interaction in under 50 milliseconds after the page is loaded. So the key thing is responding in under 50 milliseconds once the page is loaded. And then there's first input delay, which is the length of time that it takes to respond to a user interaction on the first time they just try to interact with a page. And that response. So the smaller your first input delay, the better, because if you've got like a 300 millisecond first input delay, that's going to kind of be this kind of interaction, right, where you're trying to click on things and nothing's happening. And so you can measure time to interactive with Lighthouse, which is like the auditing tool that's it's now built into Chrome. But first input delay is a little bit more tricky because you kind of you have to inject some JavaScript in before your page is kind of is ready. So you have to inject a little JavaScript snippet into your page so that it can register before all of your JavaScript event handlers have registered. But you can do that by installing, like, there's a little code snippet. You can just use a CDN, or you can use npm. Just download the first input delay package, which is from the Google, like the Chrome Labs team. So we've talked a bit about this kind of initial, what's happening on like the initial page load and kind of the problems that can occur there. But I kind of want to delve more into what's actually happening at that kind of execution stage and throughout the later life cycle of a page. And kind of in order to do that, we kind of have to talk a little bit about something called the main thread. And the main thread is the like core thread of execution where kind of all your JavaScript work is taking place. Any kind of JavaScript code that you write is generally going to be taking place like on this thread. And generally, the easiest way to think about this is just kind of this, this main thread is like an event loop. And the event loop is kind of just spinning around and taking into account all these incoming tasks that are happening. So handling user input, handling timers, handling fetch responses, doing state management, updating the DOM, updating your styling. Like pretty much everything is happening just on this main thread in this event loop. And we kind of, the event loop kind of has to interleave all these things in a sequential and sensible way so that we can, the user can do the things that they need to do. So kind of more formally, this is a diagram which I took from Jake Archibald's, did a talk at JSConf Asia, and he had this really fantastic diagram which I've borrowed from him. But you can essentially think of this event loop as this two-sided loop, and on one side you have the task queue where you have JavaScript tasks coming in, so that may be responding to a user interaction like an event handler, or it could be like a timer, or any kind of JavaScript task that gets queued. And on the other side you kind of have the render steps. So first talking about the task side of things, when the event loop encounters a task, that task is just going to run to completion. So if you have an incredibly long-running task, it's just going to block until that task is finished, and then it can yield back to the event loop. And then, so obviously, like in the browser, we need to update the screen, right? So after a certain period of time, we need to yield to the browser's rendering steps so that we can actually render and paint something to the screen. So we're going to do the styling of the page, and the layout, and then we're actually going to commit that to the screen and paint it. So yeah, that's kind of this. That's the kind of two sides to the event loop. So now I want to talk a little bit about what that kind of looks like in code in code land. Before diving directly into the code, I just want to point out that, like, I was talking that the render loop is trying to paint frames, and we need to update the screen. So, on average, like, the browser's trying to render a frame every, we're trying to render 60 frames per second. So that's 60 frames every 1,000 milliseconds, which roughly gives us about 16 milliseconds to paint a frame. It's actually slightly less than this because we have to account for things like garbage collection, but it's a good kind of ballpark figure for the amount of time that we have in each frame, like the allowance that we have in each frame to do work. Because otherwise you kind of end up in this scenario, which is where you can have, like I was saying, that the event loop, the tasks will block. So if you have like a long-running task, then it will you will skip frames for every time that you go over that frame budget. And two things happen when you have a blockage, right? So the first of which is you can't render a frame, but the second of which is that you can't respond, you can't handle user interactions. Those are just going to get queued up, which is not a great thing for users. So like, how can we address this? So like the first thing we could do, maybe like a bit simplistic here, but is just to do a set timeout. And the thing about we can like is take all that work and chunk it up and put it in a set timeout. And this is kind of okay. Like it's going to break up that work and schedule it into new tasks, which means that at least the browser at least we can yield to the browser now, and we don't just have this big long blocking tasks. We have a bunch of smaller tasks that we can render in between. But this is kind of can be problematic, especially when we're doing things like DOM updates, because if that timeout fires at the end of a frame, then we might end up having to skip a frame because we've gone into the next frame budget. So this is it can kind of lead to especially in things like animation, it can be quite like janky and quite a not fantastic kind of user experience. So there's an API called Request Animation Frame. And Request Animation Frame is pretty cool because it allows you to schedule work just before the frame commit. So you can essentially like do all your DOM updates just before the frame paints, which is great. It kind of ends up looking a little something like this, where you have all of your work is just chunked up and put in each frame budget. So that's request animation frame. So the last one, kind of scheduling API that I want to talk about is request idle callback. Probably like the least well known of the scheduling APIs, but it's kind of like this generic mechanism for scheduling, often like low priority work, but you could use it to do kind of any kind of work in theory, to schedule work when the browser has idle times, when the browser just has spare moments where it's not doing anything else. So this is great, for example, like if you wanted to schedule like analytics or anything that's not like a immediate high priority update. So another example might be like fetching some data for something that is off screen or something like that. And yeah, you can also provide a timeout. So after, for example, here, after 2 seconds, it's going to say, all right, well, if you don't have idle time, just schedule it for whenever it's next available. And yeah, this is pretty cool. And the other nice thing is like you can also cancel these requests. So if you later on realize that you don't need to do that work, you can just say, all right, we'll just cancel it. So request idle callback has support on all major browsers except Safari and like the older version of Edge, so like non-Chromium Edge. But once like Chromium-based Edge is kind of live, then it will just be Safari. But there are polyfills for this. So the React code base actually has a polyfill for request idle callback in the code base. And there's also ones that are just available on NPM. So the next thing I kind of want to come on to is this higher level concept of kind of scheduling. And scheduling is kind of an approach that we've seen gain kind of more traction inside web applications and inside frameworks as well. So what kind of is scheduling? So the core premise of scheduling is that like if you have a series of tasks that you need to complete, like some tasks might be a higher priority than other tasks. So for example, handling user interactions might be a higher priority task than some kind of extra animation that we don't need, or again, like sending analytics or some other kind of lower priority work that we need to do. So ultimately, the way I like to think about scheduling is prioritizing work in a way that is beneficial for the user. Because all that work needs to get done, but the user might not care, or it might, a user might think, might want something more to happen more quickly than something else, for them at least. So a great example of this is in Google Maps. So Google Maps actually has its own scheduler that they've implemented, and it uses, under the hood, it uses request animation frame. And it kind of groups work into 4 separate categories. One is input, the other is animation, the other is rendering, and then they just have this generic catch-all thing, like group called other. And this is quite cool because it allows them to do some clever stuff. Like, for example, like when you're panning and moving the map in Google Maps, in the background, it's also downloading and fetching tiles from the surrounding area and like loading those into memory, so that when you pan to them, they're already there and it's just instantaneous. And it feels snappy. But one thing that they can do with a scheduler is that they know, for example, if you're interacting with the left-hand side panel there, or you're interacting with a restaurant, you probably don't necessarily need to be doing all that extra work because you're trying to interact with this this component on the left-hand side of the page. So it can essentially stop doing that and then prioritize interactions with the user interface rather than with the map. And they can also do things like they can throttle the frames per second, so that you can spend less time rendering and more time doing other work. So for example, they do this at startup, so that it can prioritize like loading everything up and booting up the like the whole like library rather than focusing on rendering at the maximum number of frames per second. So there's also frameworks that are also using the concept of scheduling inside their frameworks now. So some examples of this are frameworks like React, Stencil, Dojo, which is a framework that we work on at SitePen. I mean, the most obvious and commonly used framework here is React, so I'll talk a little bit about that. So I'm not Dan Abramov, so I hope that I can do this justice. But in the latest version of React, there's this kind of idea of concurrent mode. And as part of this, they have this idea of this thing called time slicing. And time slicing is a way that allows, it's like a generic mechanism that allows React to prioritize work or tasks to make sure that high priority tasks don't get blocked by lower priority tasks. So a bit more granularly, this means that you can do updates, you can split computations of computing updates for child components during idle time, and then that rendering work can be spread across multiple frames. What this leads to is that you can kind of have these adaptive kind of user experience. So on a high-end device, it will feel very synchronous, and it will just everything will feel very smooth. And on lower-end devices, it allows them to at least have it so that your like React application is responsive, so that when the user's like interacting with the page, at least something is happening, or it feels like there is a response, even if it's not super smooth. It doesn't just block, which is cool. So yeah, this is kind of like an example of how frameworks are using scheduling. And it's kind of going a step further than that now, which is kind of exciting, is that we're moving to this place where scheduling could actually be something that's kind of built into the browser as a browser API. So in 2018, there was a W3C technical plenary and advisory committee meeting, which is quite a mouthful. And some engineers at Google basically gave a presentation about like high-level requirements for scheduling, which is kind of a little bit like what I was talking about before about like what scheduling is and what kind of the reasons that we need it. And they gave this presentation, and there's a GitHub repo that you can see on online about like how like what that might actually entail, and like what the use cases are and things like that. And kind of alongside this, in April, Facebook announced that they were working with Chrome on a scheduling method called isInputPending. And the use case for isInputPending is pretty cool. It's basically like saying, well, if we know that the user has interacted with the page, then we can yield our scheduler to handling the user interaction. And if not, then we can just go back to doing whatever it was that we were doing, like reconciling the DOM, or I'm not quite sure what React does under the hood, but it can go back to doing whatever it is that it needs to do. And yeah, so this is like this new API that they're working on. So that's pretty cool. And this could potentially lead to other APIs that will all be into this kind of scheduling namespace, which is kind of exciting. So next thing is all about web workers, because obviously one good way to not put work on the main thread is to put it on another thread. So what are web workers? I just like this simplified definition that I took off MDM, which is web workers make it possible to run a script in a background thread, allowing the main thread to run without being blocked or slowed down. And the cool thing here is that we are taking our work off the main thread. So the main thread is capable of just being idle and just being able to handle user interactions and keep updating the screen. So what does that actually look like in practice? So I've got this basic example of what web worker code looks like. So we just do a bit of feature detection. This probably isn't necessary if you're just supporting modern browsers, but I've put it in there anyway. We can create a new worker. So we have an external, all workers have to be in an external script. And so we pass in the path of the script to the worker constructor. And then in this case, we just have some DOM node that we're adding a click handler to. And when we click, we're going to send a message to the worker with some data. This, in this instance, is just sending a clicked message. And then we also have to add a event listener for when the result gets sent back to the main thread from the worker. So we've done that there. We just add an event listener to the worker, and when it comes back, it's gonna just log out that it's come back. So on the worker side, we do self.add event listener. So self is just like the equivalent of window in worker land. And when that message comes back, when that message comes to the worker, we're just going to log it out, and then we're just going to send back that we've received the message. So this is like the literal bare bones, the simplest web worker example I could possibly create. But you can pass all kinds of things over that boundary, and you can basically do anything that's not touching the DOM inside the worker. I'll come a little bit more onto the limitations in a few slides. But before that, I kind of want to touch on something which I think is really cool, which is this concept of like inline workers. So as I was saying, workers require that you have your script in a separate file, right? But some clever people essentially worked out that you can create a data URL using browser APIs like blob, URL to object URL, and you can create this inline worker, so you don't have to create a separate thread. You can just create workers on the fly from the main thread. And a guy called Jason Milner, who you might know from, he was the creator of Preact, now works at Google. But he created this library called Greenlit, and the Greenlit's really cool because essentially what it allows you to do is take an async function and just turn it into a worker, and then you can just await it like you are just awaiting a promise. You're awaiting a response from the worker. So you can treat like async functions as like functions that just run on like a separate thread, which I think is super powerful. This is just a really basic example of just fetching some data from the GitHub API, but you can do quite a lot of stuff in there if you want to. But I think it would be disingenuous of me to say that web workers will solve all your problems, because it's not necessarily true, because they have some limitations. So limited transfer types. So there's this thing called the structured clone algorithm, which is basically limitations on like things that you can pass between the worker boundary. So for example, you can't pass things like functions, or you can't pass errors or regexes or anything that isn't just like essentially basic types. So yeah, you can't transfer everything over that boundary. The other thing is transfer times, because you have to copy the data from the main thread to the worker thread memory. So you do have this cost of transferring data. And the last one, which is pretty constraining, is that you can't access the DOM, because it would lead to like race conditions and all kinds of ugly things. And so this can be obviously quite problematic for some people, because it basically just leads itself to being like just useful for kind of computations. But there is kind of an interesting workaround about this DOM limitation, which I think is interesting, which is this project that comes from the AMP team at Google, and they've worked on this thing called worker DOM, which is quite interesting, because what it does is it basically like mocks out the DOM API, so that you could write code like you normally would, like DOM touching code in your worker. And then what it does is just proxies all of those updates to the main thread. So with stuff like this, you can end up like, in theory, you could run like React like in a worker, and it would just proxy the updates to the main thread. But yeah, I just thought that's quite interesting, like quite obviously the DOM code is still running on the main thread, but for all intents and purposes, it feels like it's not. You can just kind of write code like normal. And another cool little thing that's kind of been coming out in recent years is this idea of worklets, which are like super specialized workers for specific tasks. So two examples that are being primarily worked on at the moment are the paint worklet, which allows you to have like a CSS property that, an image for a CSS property that just can be created programmatically, like inside a worker, which is cool. And also, like another example, audio worklet, which allows you to do audio processing in the browser. I'm not like a audio nerd, so I don't know too much about that side of things, but it's interesting if you're kind of working in that space. So, it talked a bit about things that users do to help, that as developers we can do to help us kind of take work off the main thread, talking a bit about web workers and worklets. But what about the browser? So the browser actually does some interesting things to try and offload work off the main thread. One of the most stark examples of this is the use of like the compositor and raster threads. So when you have your DOM tree, the browser will transform this into a kind of a series of layers. And those layers can be rasterized by the compositor thread, and then they get sent over to the raster threads, and these will commit that to the GPU memory. And having these in separate threads is quite powerful because it means that certain operations mean that you don't necessarily have to go through the whole render step process. So for example, CSS transform, so like scale, rotate, opacity, all these kind of CSS properties mean that you don't have to go through that whole the whole process of all of the render steps. You can skip most of them, and most of that work that does happen will just be offloaded to the compositor thread, which is cool because it means that we're just trying to move more and more work off of this main thread. Another example of this is moving parse and compile off of the main thread too. So Chrome's been working on this. So this is just some data that they found they found from Facebook's website, which is that once that they implemented this off main thread parse and compile, they could move 70% of that parse and compile to the worker thread, which is cool. So there's this kind of constant movement to try and offload work from the browser's trying to offload work from the main thread for us within the browsers. So yeah, kind of closing thoughts, I think. So my first kind of major point is avoid blocking users. So there's ways to do the same work, but in ways that are more users will appreciate more. So the core things here are thinking critically about the amount of JavaScript we're shipping, trying to ship as little JavaScript as possible, because obviously this seems to be like an increasing trend that we're shipping more and more. The next thing is avoiding super long-running tasks. So we don't really want tasks running over sort of 50 milliseconds if we can avoid it. And then my last point is about trying to be sensible about like how we do work. So, for example, trying to offload work where we can to another thread, for example, using web workers, using request animation frame for DOM updates, and using request idle callback when we just have low priority work that we don't necessarily need to execute straight away. Next thing I want to say is use metrics to kind of track this and see how changes to your JavaScript bundle are affecting end users in metrics like time to interactive or first input delay. And the last thing is that browsers are doing some really cool stuff, both in trying to move stuff off of the main thread, but also in trying to standardize scheduling so that we can, as developers, that we can try and be more sensible about like how we schedule work. And then the last point is just about that frameworks are also trying to be clever about like how work is scheduled. So React's doing this, and Stencil, and like I said, Dojo is doing this too. So they're implementing their own schedulers to improve user experience. And hopefully over time, they will be able to use more of these standardized scheduling APIs like isInputPending, which I talked about earlier. Yeah, thanks.
Thank you, James. I have one question. Where did you learn English so good? I want to speak so good like
England?
you.
I grew up in a town called Bath, which is a small town.
I have to move there.
Okay.
So, questions from our community. What is better? Oh, just switched.
That's okay.
We have voids here, and they just switched. Okay, what is better? Single JS bundle, let's say up to 500 kilobytes, then executes just at the beginning, or same application split it into multiple chunks?
Yeah, I mean, by and large, multiple chunks is probably the best way to, like, so with Webpack and a bunch of bundlers, you can do code splitting. So you can do things like dynamic imports so that you're only importing code when it's actually executing. So your initial bundle will be quite small, but then when, for example, you change route or you change page, then it will import a JavaScript that's like necessary for that page. So yeah, I would recommend code splitting.
Anyway, even if one bundle really small.
Yeah, I mean, obviously, if your initial bundle is small, then this code splitting is probably not really worthwhile. Like, if your bundle's under, like, I don't know, I'm just picking a number out the air, but if it's less than, say, like 30, 40 kilobytes, then it's probably
I guess
not worthwhile.
it's pretty obvious question, but I have to tell it because it's on the top. So another question, macro tasks and micro tasks.
Yes.
How it work in browser event loop? What's the difference for Node.js?
So macro tasks are generally coming from like timers or event handlers, and micro tasks are scheduled by so if you have a promise like within a task, that will schedule like a micro task, and then so micro tasks are interesting because they run after the current task is executed, but they will just keep appending to the end of that task. So if you keep scheduling promises within inside a task, it will just never necessarily end. I think like also mutation observers schedule a micro task as well, and I think maybe some other random browser APIs also schedule micro tasks. So, but the core one is promises.
Okay, thank you. And what about Node.js?
I mean, it's very like the event loop is the same, so
okay.
it doesn't make any difference really.
Okay, what you can suggest to use for prioritizing tasks in a single page application made using React?
Yeah, I mean, so the thing is with React is you probably, because they're moving to this, I'm not a React expert, by the way, so I don't use React all so much, but because they're moving to this, what's it called, concurrent mode, their whole point is to try and schedule work for you so that you don't have to. But obviously, you're still going to have your your logic with inside your components or whatever. So it depends like what you're trying to do. If you're just trying to schedule a few like simple like small tasks, then you can just run request idle callback inside the components. I would think maybe that there might be Dan Abramov might disagree with me there. I don't know. I don't know enough about React to comment too much. But
and how to get Google Dev Expert title?
It's quite a long process. So you have to have somebody recommend you, and then you have to have a meeting with a regional lead, and then you have to have an interview with a current developer expert, and then you have to have an interview with somebody at Google, and then you can become a developer expert.
Big work, yeah, really. And one more question: how many speakers need to explain to a junior an event loop?
Just one, I guess.
I guess I can add something. I guess it depends on the quality of speaker, really. You can take 10 not so good speakers and it will not work. And one more question from me: Arsenal or Chelsea?
This is where I let everybody down because I'm not a huge football fan. So,
okay, fair
sorry.
enough. Okay, thank you.
Yeah, no,
thanks to James. And which question do you think was the best for you?
I quite like the bundle question. That was
About
nice.
bundle. Богдан. Есть здесь Богдан? Кто Богдан? Про бандл спрашивал. Подождите, ребятки, не расходитесь, есть пару объявлений. Стойте. Воу. Первое объявление. Обеды будут сегодня на этажах, будут бутерброды разложены. Второе объявление. К сожалению, у нас один спикер заболела, Саша Калинина. На втором этаже должна была в 3 часа выступать. Вместо нее будет выступать, сейчас я вам скажу, да, что ж такое. Вместо нее выступит Наташа Теплухина, расскажет про магию RX